Welcome back. Today we're going to do some math and some science. Not a lot, but we need to have a scientific basis for understanding the performance of our algorithms to properly deploy them in practice. So today we're going to talk about how to observe performance characteristics of algorithms. We're going to look at how to make mathematical models and how to classify algorithms according to the order of growth of their running time. We'll talk a bit about the theory of algorithms and also how to analyze memory usage. So to put this all in perspective, we're going to think about these issues from the point of view of different types of characters. So the first one is a programmer who needs to solve a problem and get it working and get it deployed. Second one is the client who wants to use whatever the program did to get the job done. Third one is a theoretician. That's somebody who really wants to understand what's going on. And the last one is kind of the team, this basic blocking and tackling sometimes necessary to get all these things done. So there's a little bit of each one of these in today's lecture. And actually, when you're a student, you have to think that you might be playing any or all of these roles someday. So it's pretty important to understand the different points of view. So the key that we'll focus on is running time. And actually, the idea of understanding the running time of a computation goes way back even to Babbage and probably before. Here's a quote from Babbage. As soon as an analytic engine exists, it will necessarily guide the future of the course of the science. Whenever any result is sought by its aid, the question will arise, by what course of calculation can these results be arrived at by the machine in the shortest time? If you look at Babbage's machine called the analytic engine, it's got a crank on it. And literally, the concern that Babbage had in knowing how long a computation would take is how many times do we have to turn the crank? It's not that different in today's world. The crank may be something electronic that's happening a billion times a second, but still we're looking for how many times does some discrete operation have to be performed in order to get a computation done. So there's a lot of reasons to analyze algorithms. In the context of this course, we're mainly interested in performance prediction. We also want to compare the performance of different algorithms for the same task and to be able to provide some guarantees on how well they perform. Along with this is understanding some theoretical basis for how algorithms perform. But primarily, the practical reason that we want to be analyzing algorithms and understanding them is to avoid performance bugs. We want to have some confidence that our algorithm is going to complete the job in the amount of time that we think it will. And it's very, very frequent to see in today's computational infrastructure a situation where the client gets bad performance because the programmer did not understand the performance characteristics of the algorithm. And today's lecture is about trying to avoid that. Now, we're going to focus on performance and comparing algorithms in this course. There's later courses in typical computer science curricula that have more information about the theoretical basis of algorithms, and I'll mention a little bit about that later on. But our focus is on being able to predict performance and comparing algorithms. Now, there's a long list of success stories in designing algorithms with better performance and enabling the solution of problems that would otherwise not be solved. And I'll just give a couple of examples. One of the first and most famous is the so-called FFT algorithm. That's an algorithm for breaking down the waveform of n samples of a signal into periodic components. And that's at the basis for DVDs and JPEGs and many other applications. There's an easy way to do it that takes time proportional to n squared, but the FFT algorithm takes only n log n steps. And the difference between n log n and n squared is the difference between being able to solve a large problem and not being able to solve it. A lot of the digital technology, digital media technology that we have today is enabled by that fast algorithm. Another example was actually developed by Andrew Appel, who's now the chair of computer science here at Princeton, and it was developed when he was an undergraduate for his senior thesis. It's a fast algorithm for the n-body simulation problem. The easy algorithm takes time proportional to n squared, but Appel's algorithm was an n log n algorithm that again meant that scientists can do n-body simulation for huge values of n, and that enables new research. So the challenge is that we usually face is, will my program be able to solve a large practical input? Actually, the working programmer is actually faced with that all the time. Why is my program running so slowly? Why does it run out of memory? And that's faced programmers for a really long time. And the insight to address this, due to Knuth in the 1970s, was that we really can use the scientific method to understand the performance of algorithms in operation. Maybe we're not unlocking new secrets of the universe, but we can use the scientific method and treat the computer as something to be studied in that way, and come to an understanding of how our programs are going to perform. And let's take a look at that in more detail. So this is just a quick summary of what we mean by the scientific method, which has been successful for a couple of centuries now. So what we're going to do is observe from some feature of the natural world. In this case, it's going to be the running time of our program on a computer. Then we're going to develop a hypothesis, some model that's consistent with the observations. And we're going to hope that that hypothesis is good enough that it'll allow us to predict something, usually predict the running time for larger problem size or on a different computer. And then we'll verify the predictions by making more observations and validate until we're comfortable that our model, hypothesis, and observations all agree. That's a way to get comfort that we understand the performance of our programs. Within the scientific method, there's some basic principles. And the first is that if you're going to run experiments, you should expect that somebody else should be able to run experiments and get the same result. And also, the hypotheses have to have a specific property that the experiment can show the hypothesis to be wrong. So it has to be carefully crafted, and we'll be sure to try to do that. And again, the feature of the natural world that we're studying is some particular computer that exists in the natural world. It changes the algorithm from an abstraction to some kind of actual physical thing happening, like electrons racing around inside the computer. Okay, so the first step is to be able to make some observations about the running time of the programs. And for analysis of algorithms, that's easier than in a lot of scientific disciplines, as we'll see. For an running example, we're going to use the so-called three-sum problem. And it's an easy-to-state problem. If you've got n distinct integers, how many triples sum to exactly 0? For example, in this file, 8int.txt, which has 8 integers in it, there's 4 triples that sum to 0. 30 minus 40, 10, 30 minus 20 minus 10, and so forth. And so our goal is to write a program that can compute this quantity for any input file, any set of n integers. This is actually an extremely important computation that's deeply related to many problems in computational geometry, which is a branch of computer science that covers the algorithms and underlying science related to graphics and movies and geometric models of all sorts. So this is actually an important practical problem, but it's a simple one to write code for. Any of you could write down this program without much effort. It's got a static method count that is going to go ahead and take an integer array as argument. N is that's the number of integers, that's the length of the array. We'll start with a variable count equals 0, and then a triple for loop that checks each triple I, j, k. We go I from 1 to n, j from I plus 1 to n, and k from j plus 1 to n, so that we get each triple just once. And then if I plus j, ai plus aj plus ak equals 0, we increment the count. And after that triple for loop, we return the count. And then the main method in this simple class just reads in all the integers and prints out the count. So that's a brute force algorithm that is a fine method for solving the three-sum problem. Now what we're interested in is how much time does this take as a function of n? Well, one way to time a program is to just look at the watch. If you have a stopwatch, or look at the clock, or your phone, whatever you might need, you can just go ahead and time it if you want. We have, Java has as part of its standard library a stopwatch class that will go ahead and compute elapsed time. Anytime you run a program, if it's set up to easily take input of different sizes, a natural thing to do is just run it for bigger sizes. So for 8 ints, this program takes not too much time. For 1,000 ints, it takes half a second. For 2,000, it takes more time. That's 3.7 seconds. Run it again, still takes 3.7 seconds. For 4,000, so each time we're doubling the size of the input, and it's definitely taking more time each time. And actually, as we'll see, if programmers who get in the habit of testing the running time of their program in this way can get so that you can actually pretty easily and quickly evaluate when it's going to finish. In fact, while you're waiting for it to finish, you can often figure it out. That one took 30 seconds for 4K, and definitely we could figure out how long it's going to take for 8K before it finishes. And you'll see how in just a second. I'm not going to wait right now. You can think about what you think. Okay, so that's empirical analysis. Run it for various input sizes and measure the running time. Now, if this were some scientific problem where we were counting something that happened in the natural world, the number of ants on an anthill or whatever, then we'd have only a few data points, and we would try to understand what's going on by doing a plot of our running time, the quantity we're interested in on the y-axis, and the problem size on the x-axis. We get a curve like this. And actually what scientists usually do, because so many problems fall into this class, is do the plot as a log-log plot. If you do it as a log-log plot, very often you'll get a straight line. And the slope of the straight line is the key to what's going on. In this case, the slope of the straight line is 3. And so you can run what's called a regression to fit the straight line through the data points. And then it's not difficult to show, to do the math to show that if you get a straight line and the slope is b, then your function is proportional to n to the b. That's called a power law. And that's true of many, many scientific problems, including most algorithms. So here's a little bit of the math for that. The straight line means that since we did a log-log plot with powers of 2, that log base 2 of t of n equals b log of n plus c. And we have our empirical values of b and c. And then if you raise both sides of that equation to 2 to that power, then you get t of n equals a constant times n to the b. Right away, just from observation, we have a pretty good model for the running time of our program. We can do the math and figure out that it seems as though the running time is about 10 to the minus 10 times n cubed seconds. And we can use that hypothesis to go ahead and make predictions. Just plug in for different values of n, and it says it ought to take us 400 seconds for 16,000. And 400 seconds is plenty of time, but now we can go ahead and invest in running that experiment, and sure enough, we're pretty close to that 408 seconds when we run it. And now we can make a prediction for 32,000 or for whatever else we might be interested in. The model helps us do predictions without investing the expense to run the experiments. In fact, in this situation, if there is a power law, and again, in very great majority of computer algorithm running times, it's going to be a power law. What we can do is just double the size of the input each time, the way we were, and then take the ratio of the running times for n and 2n. And if you do that, that ratio is going to converge to a constant. And in fact, the log of the ratio is going to converge to that constant, which is the exponent of n in the running time. And just need a little math to check that one, but that's a very easy and natural way to go ahead and predict running times. So that's what I said before is, so we have this quick way to estimate B in the power law relationship. How do we estimate A? Well, we can just run it and solve for A. So once we've decided that that exponent is 3, let's run it for some big N, and we get a pretty close model to the one we had from plotting things. So it's almost identical hypothesis, and we just got it by running the program doubling n each time. Okay, so there's a lot of effects in trying to understand the running time of a program on your machine. So key effects are independent of what computer it is, and that's the algorithm you're using and what's the data. And that's going to really determine the exponent in the power law. And then there's a lot of system-dependent effects. What kind of hardware do you have? Do you have a fast computer or a slow one? What kind of software? What's going on in your computer? All of those things really determine the constant A in the power law. So in modern systems, there's so much going on in the hardware and software, it's sometimes difficult to get really precise measurements. But on the other hand, we don't have to sacrifice animals or fly to another planet the way they do in other sciences. We can just run a huge number of experiments and usually take care of understanding these kinds of effects. Observing what's happening, as we did in the last section, gives us a way to predict performance, but it really doesn't help us understand what the algorithm's doing. So next we're going to look at mathematical model, a way to get a better concept of what's really happening. Again, this concept was really developed and popularized by Don Knuth starting in the late 60s. At that time, computer systems were really becoming complicated for the first time, and computer scientists were concerned about whether we really were going to be able to understand what's going on. And Knuth was very direct in saying that this is something that we certainly can do. We can calculate the total running time of a program by identifying all the basic operations, figuring out the cost, figuring out the frequency of execution, and summing up the cost times frequency for all the operations. You have to analyze the program to determine what set of operations, and the cost depends on the machine and the computer in the system, is what we talked about before. The frequency leads us to mathematics because it depends on the algorithm and the input data. Knuth has written a series of books that give very detailed and exact analyses within a particular computer model for a wide range of algorithms. So from Knuth, we know that in principle, we can get accurate mathematical models for the performance of algorithms or programs in operation. All right, so what does this process look like? You can, if you want, run experiments. In ancient times, we would actually look at the computer manual, and every computer came with a manual that said precisely how long each instruction would take. Nowadays, it's a little more complicated, so we run experiments. You can go ahead and do a billion ads and figure out that maybe on your computer an ad takes 2.1 nanoseconds. Or you can do more complicated functions like compute a sign or an arctangent, although that's already getting close to the analysis of algorithms. So there's some way to determine the cost of the basic operations. So we'll just, in most of the cases, we'll just postulate that it's some constant, and you can figure out what the constant is. Although when we're working with a collection of objects, of n objects, there's some things that take time proportional to n. Like if you're going to allocate an array of size n, it takes time proportional to n because in Java the default is that all the elements in the array are initialized to 0. In other operations, it depends on the system implementation. And an important one is string concatenation. If you concatenate two strings, the running time is proportional to the length of the string. And many novices programming in Java make the mistake of assuming that that's a constant time operation when it's not. All right, so that's the cost of each operation. More interesting is the frequency of operation, of execution of the operations. So this is a very simple variant of the three-sum problem. That's the one-sum problem. That's how many numbers are actually equal to 0, how many single numbers add up to 0. So that one is just one for loop, and we go through and we test if the number is 0 and increment our count. And by analyzing that code, you can see that I and count have to be declared, and they have to be assigned to 0. There's compares of I against n, and there's n plus 1 of them. There's compares of a of I against 0. There's n of those, n array accesses. And the number incremented is, number of times as an increment is variable. I is incremented n times, but count could be incremented any number from 0 to n times. And so that frequency is dependent on the input data. We might need a model for describing that, or maybe there's other operations that are more expensive and we won't need to worry about that. So let's look at the next more complicated problem is what about the frequency of execution of instructions in this program, which is the two-sum problem. How many pairs of integers sum to 0? Well, in this case, you have to do a little bit of math to see that when I goes from 0 to n and j goes from I plus 1 to n, the number of compares that we do, or let's say array accesses that we do, is 2 for each time the if statement is executed for ai and aj, and that time thing is executed n minus 1 times the first time through the loop and n minus 2 the second and so forth. It's the sum of the integers from 0 up to n minus 1, which is a simple discrete sum, 1/2 n times n minus 1, and since we're doing it twice, the number of array accesses is n minus 1. So we can go ahead and get these actual exact counts, but already it's getting a little bit tedious to do that. As far back as Turing, who also knew that, as well as Babbage did, that we want to have a measure of the amount of work involved in the process, he recognized that you didn't want to necessarily go through and do it in full detail. It's still helpful to have a crude estimate. So you could count up the number of times that every operation is applied, give it weights, and count this abstract and so forth. But maybe we should just count the ones that are most expensive. That's what Turing said in 1947. And realistically, that's what we do nowadays. So rather than going in and counting every little detail, we take some basic operation that's maybe the most expensive and or the one that's executed the most often, the one that cost times frequency is the highest, and use that as a proxy for the running time. Essentially making the hypothesis that the running time is going to grow like a constant times that. So in this case, we're going to pick array accesses. So that's the first simplification. And the second simplification is that we're going to ignore low-order terms in the formulas that we derive. And there's an easy way to do that. It's called the tilde notation. And the idea is when n is large in a formula like this, the n cubed term is much, much higher than the n term, or 16. In fact, so much so that we wouldn't even would hardly notice these low order terms. So all of these formulas are tilde 1/6 n cubed. And that's a fine representative or approximation to these quantities. And it greatly simplifies the calculations to throw away the low order terms like this. So by focusing on one operation and throwing away the tildes, the low order terms, and this is the technical definition of tilde, it just, f of n tilde g of n means the limit as fn or gn equals 1, and you can check that that's going to hold in these kinds of situations. So that greatly simplifies the frequency counts, and if we're only picking one thing, we're just talking about tilde n squared and maybe another tilde n squared for the increment for the two-sum problem, say. So again, when n is large, the terms are negligible. When n is really small, they're not negligible, but we don't really care because we're trying to estimate running times for large n, and running times for small n are going to be small no matter what. All right, so now we're using both the cost model and the tilde notation, and we can simply say that this program uses tilde n squared array accesses and have implicit the hypothesis that we think the running time is going to be tilde a constant times n squared. Okay, well now what about three-sum? Let's do our real problem. So now we have the triple loop, and then we have to do a more complicated combinatorial problem. And it's not that big a deal, really. We're looking at the distinct number of ways you can choose three things out of n, and that's the binomial coefficient. And again, doing the math and using the tilde, it's just tilde 1/6 n cubed. 3 array accesses for each triple, so we can say half n cubed. We're not computing and summing the costs of all operations. That's too much work. We're picking the most expensive in terms of cost times frequency and approximating that and trying to get a good model for the running time. Now we're not going to do a full discrete mathematics in this course, but there's some basic things that we'll want to use and are not that difficult to understand. So a lot of times we find out that we need to come up with an estimate of a discrete sum, like we did for 1 + 2 up to n, or some of the squares, or other things like the three-sum triple loop. And so actually, if you've had basic calculus, one way to think of it is to just replace the sum with an integral. That usually works, or we can do the math and use the so-called Euler-Maclaurin summation formula to get a true approximation. But if you think of it this way, you'll believe us when we say that that thing is tilde half n squared, or sum of 1 + 1/2 + 1/3 up to 1 over n. That's like integral from x = 1 to n 1 over x, and that's natural log of n. Even the three-sum triple loop, if you're used to multiple integrals, will quickly give you the 1/6 n cubed. There's many more and other techniques that we could use for this, and we're not going to teach all that, but we'll sometimes refer to results of this type. All right, so in principle, Knuth tells us that accurate mathematical models are available. In practice, we can get really complicated formulas. We also might need some advanced mathematics that the theoretician will revel in, but that maybe people learning algorithms for the first time might not be expected to know. In the end, careful, exact models are best left for experts. There's really a lot of things that can go on. On the other hand, approximate models are definitely worthwhile. And for all the algorithms that we consider, we'll try to communicate a reasonable approximate model that can be used to describe the running time. Sometimes we'll give the mathematical proofs, and other times we'll have to just cite the work of some expert. Now, fortunately, when we analyze algorithms, actually not too many different functions arise. And actually, that property allows us to really classify algorithms according to their performance as the problem size grows. So that's what we'll talk about next. So the good news is there's only these few functions turn up about the algorithms that we're interested in. We can craft things that have other functions, and there are counterexamples to this. But really, a great number of the algorithms that we consider are described by these few functions that are plotted here. When we're talking about order of growth, we're not talking about the leading constant. Normally we'll say the running time of the algorithm is proportional to n log n. That means we think that our hypothesis is that the running time is tilde c log n, n log n, where c is some constant. And in these plots, these are log-log plots that really give a good idea of what's going on. If an order of growth is logarithmic or constant, it doesn't matter how big the thing is, it's going to be fast. If the running time is t for, say, 1,000, then for 500,000, it'll be pretty close to t. If it's linear, if its order of growth is proportional to n, then as the running time, as the size increases, the running time increases correspondingly. And the same is true almost if it's n log n. So those are the algorithms that we strive for. They scale with the input size. As the input grows, so grows the running time, and that's a reasonable situation to be in. As we talked about when we talked about union find, if it's quadratic, the running time grows much faster than the input size, and it's not feasible to use such an algorithm for large inputs. And cubic is even worse. So what we find is for many algorithms, our first task is really simply make sure it's not quadratic or cubic. And these order of growth classifications actually come from kind of simple patterns in terms of the code that we write. So if our code has no loops in it, then the order of growth is going to be constant. If our code has some kind of loop where the input's divided in half, and so binary search algorithm's an example of that, then our order growth will be logarithmic, and we'll take a look at that analysis. But if you do the doubling test, it grows almost linearly. If you have a huge input and you double the size, it's still going to be, I'm sorry, not linearly, constant, just like if it's constant. You'll hardly notice that log n. If you have a loop where you touch everything in your input, then the running time is linear, proportional to n. So a typical example of that would be find the maximum or count the number of zeros, our one-sum problem. A very interesting category is the so-called n log n algorithms or linear arithmetic algorithms. And those are the ones that arise from a particular algorithm design technique called divide and conquer. And the merge sort algorithm, which we'll talk about in a couple of weeks, is a prime example of that. And then if you have double for loops, like our two-sum algorithm, that's going to be time proportional to n squared, as we saw. That's quadratic. Or triple for loop, like our three-sum algorithm, that's going to be cubic, or time proportional to n cubed. For a quadratic algorithm or a cubic algorithm, the doubling factor is 4 or 8. As the input size doubles for a cubic algorithm, the running time goes up by a factor of 8. And that's the kind of calculation you can do in your head while waiting for a program to finish. There's also a category of algorithms whose running time is exponential. And in those algorithms, n doesn't get very large at all. And we'll talk about those at the end of part 2 of the course. So these are some practical implications of the order of growth. And I won't really dwell on this too much, except to come back to the point that the algorithms that we're really interested in that can solve huge problems are the linear and n log n algorithms. Because even now, a quadratic algorithm on a typical fast computer could only solve problems in, say, in the tens of thousands, and a cubic algorithm only in the size of thousands. And nowadays, those are just not useful because the amount of data that we have is more like the millions, billions, or trillions. That fact is becoming more and more evident as time wears on. In ancient times, we'd have some discussion about whether a quadratic algorithm might be useful, but the situation gets worse as time gets on, so we need better algorithms. To illustrate the process of developing a mathematical model for describing the performance of an algorithm, we'll look at a familiar algorithm called binary search. The goal is that you have a sorted array of integers, say, and you're given a key, and you want to know, is that key in the array? And if it is, what's its index? And a fast algorithm for doing this is known as binary search, where we compare the key against the middle entry. In this case, if we're looking for 33, we compare it against 53. If it's smaller, we know it's in the left half of the array. If it's larger, we know it's in the right half of the array. If it's equal, we found it. And then we apply the same algorithm recursively. So let's quickly look at a demo. So we're looking for 33 in this array. We compare it against the middle entry in the array, 53, and it's less, so we go left. So now we can concentrate just on the left half of the array. Now we look in the middle of this half, that's 25, 33 is bigger, so we go right. Now we concentrate on the right half of the left half, and we have a smaller subarray. Look at the middle, 33 is less, so we go left. And now we have only the one element to look at, and we found our key 33 in the array, and we return that index 4. If we're looking for something that's not in the array, we do the same process. So say we're looking for 34, it's going to be the same. Look in the left half, look in the right half, look to the left of the 43. Now there's only one key to look at, and it's not 34, so we say it's not there. So that's binary search. So here's the code for binary search. Binary search, although it's a simple algorithm, it's notoriously tricky to get every detail right. In fact, one paper claimed that the first bug-free binary search wasn't published until 1962. And even in 2006, a bug was found in Java's implementation of binary search. Just an indication of the care that we have to take in developing algorithms, especially for libraries that are going to be used by millions of people. So here's an implementation. It's not recursive, although often we can implement this recursively. and it's just reflects in code what I described in words. If we have to find whether keys in an array, we use 2 pointers, low and high, to indicate the part of the array that we're interested in. As long as low is less than or equal to high, we compute the middle, and then we compare our key against the middle. Actually, it's a 3-way compare. It's either less or it's greater. Or if it's equal, we return that mid-index. If it's less, we reset the high pointer. If it's greater, we reset the low pointer, and we keep going until the pointers are equal. And if they're equal and we haven't found it, then we return -1. And it's easy to persuade ourselves that this program works as advertised by thinking about this invariant. If the key is in the array, then it's between low and high in the array. All right, so that's a program that you're probably familiar with. Let's look at the mathematical analysis of that program. And this is a theorem that we're going to prove. We usually, we won't do a lot of proofs, but this one's worth doing. So it says that binary search uses at most 1 plus log base 2 of n compares to complete a search in a sorted array of size n. So we do that, set up the problem by defining a variable t of n, which is the number of compares that binary search is going to need for an array of size n. And then we write down a recurrence relation that reflects the code. And what the code does is it divides the problem size in half so that t of n is less than or equal to t of n over 2. Plus, depending on how you count what the compare is, think of it as really a 2-way compare. So divide it in half by doing 1 compare. And that's true as long as n's bigger than 1. If n's equal to 1, the solution is 1. So that's a recurrence relation describing the computation. And so we can go ahead and solve this recurrence by applying the recurrence itself to the first term on the right. That's called telescoping. So if this is true, then we can apply the same thing to t of n over 2 and throw out another 1. And if this is true, we can apply the same thing to n over 4 and throw another 1, and so forth, until we get down to just 1, in which case we have log n 1s left. Now, this is a proof sketch. You might have noticed that this proof actually only holds if n is a power of 2, because we didn't really specify in this recurrence what we mean if n is odd. But it's possible to go ahead and, possible to go ahead and take care of that detail as well and show that binary search running time is logarithmic always. All right, so given that fact, we can develop a faster algorithm for 3-sum. It's a sorting-based algorithm. And so what we're going to do is we're going to take the numbers that we have as input and sort them. We'll talk about sorting algorithms next week. And we can get that done in time proportional to n log n, but that's not the main part of the computation. The main part of the computation is after the numbers are sorted, we'll go through and for each pair of numbers, AI and AJ, we'll do a binary search for minus AI plus IJ. If we find it, then we have 3 numbers that sum to 0. So we sort our numbers and then go through for each pair, do a binary search to see if it's there. So minus 40, 0, minus that is 40. We do a binary search that's in there. So we have one solution to the 3-sum problem. And do that for all pairs of numbers. Then a quick analysis says the order of growth of the running time is going to be n squared log n. You don't even need a good sort. You could use the elementary insertion sort, the first one we talk about. But the running time of the binary search for each of the pairs, each of the n squared pairs, or n squared over 2 pairs, we're going to do a binary search, so we get an n squared log n running time. So it's a quick example of how we can improve the performance. We can find an improved algorithm to solve a problem. N squared log n is much less than n cubed for large N. And so we're implicitly making the hypothesis that if we do this sort-based thing and use binary search, we're going to have a faster program. And sure enough, we can go ahead and run some experiments and find that whereas it took us 50 seconds to solve the problem for 8,000 numbers before, it's taking less than a second now. In 50 seconds, we can solve up to 64,000. So typically, we expect that better order of growth means faster in practice. But when it comes to examining the algorithms in detail, we can go ahead and do the tests and figure out which algorithm is faster. And certainly, going from n cubed to n squared log n, we're going to expect that we're going to have a much better algorithm. In fact, order of growth classifications are so important, they've led to an enormous amount of research in recent years, and we'll just talk briefly about that now. Life is a little bit more complicated than pointed out in the last example. And one problem is that the inputs can cause the performance of the algorithm to vary widely. So often we have to think about different ways of analyzing the algorithm depending on the input. So the running time is going to be somewhere between the best case and the worst case. Best case is a lower bound on costs. It provides something that the running time is going to be bigger than that always, or not less than that. And then there's the worst case, which is the most difficult input. If we analyze that, then we can guarantee that the running time of the algorithm's not going to be bigger than that. And then in a lot of situations, we might consider our input to be random. Well, we need some way to model what we mean by random for the problem that we're solving. But there's a lot of situations where we can do that, and then we have a way to predict performance. Even when the input might vary widely. So for example, for threesome, it's kind of always the same. With the tilde notation, the only variability in that algorithm is the number of times the counter is incremented, and that's in low order terms, so it doesn't even show up in our analysis. For binary search, you might find the thing right away, in which case it's constant time, and we can show that the average in the worst case are both log base 2 of n. And there's in other examples there'd be much more variability even. We have these different types of analyses depending on the input, but the question is, what about the actual problem that the client's trying to solve? So we have to understand that too in order to be able to understand performance of the algorithm. And there's two approaches that are successful in this. One is to design for the worst case. Just make sure your algorithm always runs quickly, and that's definitely ideal. Another is to, if you can't do that, is to randomize and then depend on some kind of probabilistic guarantee. We'll see examples of both of these as we go through the course. Now, those kinds of considerations and the idea of order of growth leads to a discussion of what I call the theory of algorithms. And here our goals are, we have a problem to solve, like solve the threesome problem, and we want to know how difficult it is. We want to find the best algorithm for solving that problem. Now, the approach that computer scientists use for this is to try to suppress as many details as possible in the analysis. And so just analyze the running time to within a constant factor. That's what order of growth is getting at. And also, we want to not worry about the input model at all, and so we focus on worst case design. Then we can talk about performance of algorithms just in terms of the order of growth. And it's actually possible to do that in a very rigorous way that has taught us a lot about the difficulty of solving problems. And our goal is to find an optimal algorithm where we can guarantee to within a constant factor certain performance for any input, because we discovered worst case. But we also can have a proof that no algorithm can provide a better performance guarantee. I'll give a couple of easy examples of this. Now, in order to do this, there are these commonly used notations called the Big-Theta, Big O, and Big Omega notations. And those definitions are given here. So the Big-Theta notation is just a way to describe the order of growth. Theta of n squared is kind of shorthand for anything times n squared. It's bounded above and below by constant times n squared. And that's what we really use to classify algorithms. And then there's big O notation, which is upper bounds on performance. When we say big O of n squared, we mean that it's less than some constant times n squared as n grows. And big omega is used for lower bounds, which means it's greater than some constant times n squared as n grows. So those three notations we're able to use to classify algorithms, and I'll show in the following. So the examples are from our one sum, two sum, and three sum are easy to articulate. So our goals are to establish the difficulty of the problem and develop an optimal algorithm. So the one sum problem, is there a zero in the array? Well, an upper bound on the difficulty of the problem is some specific algorithm. So, for example, the brute force algorithm that looks at every array entry is a specific algorithm. And it means that, and that takes O of n time. You have to look at it's less than a constant times n for some constant. So the running time of the optimal algorithm has to be O of n. That is, that specific algorithm provides an upper bound on the running time of the optimal algorithm. But in this case, it's also easy to develop a lower bound. That's a proof that no algorithm can do better. Well, for one sum, you have to examine all entries in the array. If you miss one, then that one might be zero. So that means that the optimal algorithm has to have a running time at least some constant times n, or we say the running time is omega of n. Now in this case, the upper bound and the lower bound match. So to within a constant factor, so that's a proof that the brute force algorithm for one sum is optimal. Its running time is theta of n. It's both omega n and O of n. That's, for that simple problem, it was okay to get the optimal algorithm. For more complicated problems, it's going to be more difficult to get upper bounds and lower bounds, and particularly upper bounds and lower bounds that match. For example, let's look at three sum. So upper bound for three sum, say our first brute force algorithm said that the proof was a proof that the running time of the optimal algorithm is O of n cubed. But we found a better improved algorithm whose running time is O of n squared log n. So that's a better upper bound. Lower bound, well, we have to examine all entries because, again, we might miss one that makes three sum equals zero. And that's a proof that the running time of the optimal algorithm is omega of n. But nobody knows a higher or lower bound for three sum. So there's a gap between the upper bound and the lower bound in open problems. Is there an optimal algorithm for three sum? We don't know what it is. We don't even know if there's a algorithm whose running time is less than O of n squared, or we don't know higher or lower bound than linear. So that's an example of an open problem in the theory of algorithms. We don't know how difficult it is to solve the three sum problem. Now, this point of view has been extremely successful in recent decades. We have a new problem, develop some algorithm, prove some lower bound. If there's a gap, we look for a new algorithm that will lower the upper bound, or we try to find a way to raise the lower bound. Usually it's very difficult to prove non-trivial lower bounds. Trivial lower bound, like look at every input item, is not so hard. Non-trivial lower bounds, like for example, the proof that we talked about for the union find problem, are much more difficult. In the last several decades, people have learned about the computational difficulty of problems by examining steadily decreasing upper bounds. So algorithms with better worst case running times for lots and lots of important problems. And plenty of optimal algorithms, and plenty of gaps still remain. It's a fascinating field of research that many people are engaged in. Now, there's a couple of caveats on this in the context of this course. And the first one is maybe it's overly pessimistic to be focusing on the worst case. We've got data out there, we've got problems to solve, maybe it's not worst case data. In lots of fields of engineering and science, we don't focus on the worst case. The worst case for this course would be for lightning to strike and it would be over. So we don't plan for that. And similar is true for algorithms. Maybe we should be focusing on understanding properties of the input and finding algorithms that are efficient for that input. And the other thing is, in order to really predict performance and compare algorithms, we need to do a closer analysis than to within a constant factor. We talked about the tilde notation in the big theta, big O, and big omega that are used in the theory of algorithms. And really, there's so much published research in the theory of algorithms that a lot of people make the mistake of interpreting the big O results that are supposed to give improved upper bounds on the difficulty of the problem as approximate models for the running time, and that's really a mistake. So in this course, we're going to focus on approximate models by making sure that we use the tilde notation. And we'll try to give specific results for certain quantities of interest, and the constant, any unspecified constant in the running time will have to do with properties of the machine and the system, so that we'll be able to use these results to predict performance and to compare algorithms. So far we've been talking about running time. Now we have to talk about the memory requirements of our programs as well. Well, the basics are we want to know how many bits the program uses, or bytes, 8 bits at a time. And actually we'll be talking in terms of millions of bits or billions of bits. And actually, surprisingly, there's controversy about even these basic definitions. Computer scientists think of 1,000,000 bits as 2 to the 20th and 1 billion as 2 to the 30th because that's the number of possible things that you can fit into the 30 bits, and everything is consistent with our calculations. Other scientists stick to 1 million and 1 billion for lots of reasons. We'll usually use 2 to the 20th to mean a megabyte. Now, on old computers, we used to, for many years, use a 32-bit machine so that pointers were 4 bytes. Just in recent years, we've mostly switched to a model where machines are 64 bits and pointers are 8 bytes. That allows us to address much more memory, but pointers use much more space. And actually, this transition caused a lot of problems initially because programs were using way more space than people thought they should. You're not going to have to go through this kind of transition the way that we did, because 64 bits is definitely enough to address anything that you might need to address. 2 to the 64th is really a huge number. In terms of bytes, we have to start out with typical memory usage. Now again, this is very dependent on machine and implementation, but these numbers are reasonable and are found on typical implementations. So a Boolean, it would be nice if a Boolean just took a bit because it's just true or false, but actually usually we have to count for a byte for a Boolean. Well, a byte is a byte. Character nowadays is 2 bytes, 16-bit characters. Not that long ago, we used 8 bits for chars. Integer, regular int is 4 bytes, or 32 bits, and float is also 4 bytes. Long int is 8, and a double is 8. Usually we use doubles for floating point and ints for integers in most applications. So that's for primitive types. And then for arrays, there's a certain amount of overhead for making an array, and then if there's n items, it's whatever the cost of the primitive type times n. So an array of doubles is, say, 8n plus 24. And two-dimensional array, then, well, we can go ahead and compute the exact thing, but now it's time to use the tilde notation. Even for arrays, we could say a double is tilde 8n for one-dimensional. For two-dimensional, a two-dimensional array of doubles is tilde 8mn. And there's extra terms for the overhead, but for large m and n, that's going to be pretty accurate. So that's our basic usage for primitive types and arrays in a typical Java implementation. Now, a lot of our programs use objects like linked lists and so forth, so we have to also factor in object overhead, cost of a reference, and also there's padding built in typical implementations to make it so that each object has to use a multiple of 8 bytes. So, for example, if you had a date object that had 3 int instance variables, then that object would take a total of 32 bytes. Each int takes 4 bytes. Object overhead is 16 bytes. You need 4 bytes for padding, so it's a total of 32 bytes. And the other one that often comes up is a string, and a string is a little bit more complicated than an array, but the typical implementation of a string in Java has a reference out to an array of characters, and then it's got int values for offset, count, and a hash value, and then some padding. And adding it all together, the cost of a string is about 2n plus 64 bytes. So these are the basics that we need to analyze the memory usage for a typical Java program. So for data type value, if it's a primitive type, it's 4 for an int, 8 for a double, and so forth. If it's a reference, it's going to be 8 bytes. That's what a pointer takes. Array, 24 bytes plus the memory for each entry, and an object, 16 bytes plus the memory for the instance variable, plus if there's an inner class, it's another 8 bytes, as we talked about with nodes for linked lists, and then there's the padding. Then we have to think about who's responsible for referenced objects in some cases, and we'll take care of that when we get to these situations. So as an example, a simple example of memory use analysis, let's take a look at how much memory our weighted quick union UF function from a few lectures ago uses as a function of n. And there's only a couple of memory elements, and each one of them are easily analyzed using the basics that we just gave. It's an object, so there's 16 bytes of object overhead. There's 2 int arrays. Each one of them have array overhead of 24 plus, and then 4n for the n entries. Each n of the n entries takes 4 bytes. And then there's 4 bytes for the count, and there's 4 bytes for the padding, and if you add it all together, it's 8n plus 88, which is tilde 8n. And again, all that's saying is when n is large, all we are going to care about in terms of analyzing the memory is that we've got 2 n integers, 2 arrays of size n, each one of which takes 4 bytes for a grand total of 8n bytes. Okay, so in summary, we really can figure out how many times we have to turn the crank on modern computers. We can do it with empirical analysis, where we actually execute the program to do experiments and assume a power law, formulate a hypothesis, and make predictions. But we can do more. We can do mathematical analysis, where we can identify the most costly operations, analyze the frequency of execution of those operations, and using the tilde notation to simplify analysis, we can actually explain the behavior, not just predict it. And this is a fine example of the use of the scientific method to understand the artifacts that we're studying, the algorithms. Our mathematical models are usually independent of a particular computer system and even applied to machines that are not yet built. But we always validate our mathematical models by running experiments on real machines so that we can be confident when we're making predictions and analyzing algorithms.